to measure just what the universe was made of. These two teams, known as the High-Z Supernova Search Team and the Supernova Cosmology Project, brought together astronomers from around the globe with the goal of charting cosmic expansion over the life of the universe. The astronomers expected the presence of all the matter and radiation in the universe to act like a drag on the expansion, steadily slowing it as the cosmos aged. By measuring this deceleration, all the matter and energy that make up the universe would be revealed. These international collaborations called on the world's mightiest telescopes, such as the 8-meter Keck telescope in Hawaii and orbiting Hubble Space Telescope, to scour the sky. Their target was supernovae, acting as beacons of the distant cosmos, whose brightness as measured through our telescopes revealed how the universe had expanded as their light travelled for billions of years. But the astronomers were in for a shock. Our universe is not slowing down. It is speeding up. After repeatedly searching for flaws in their observations and checking their calculations, they presented their conclusions to a startled world. And to account for this accelerated expansion, there was something else in the universe, something unexpected, driving the cosmos faster and faster. And whilst there must be immense quantities of this stuff for the effect to take place, it remained and remains totally invisible to our telescopes. Whatever is out there, between the stars and galaxies accelerating the expansion, it is truly dark. This result netted the leaders of the experiment, Brian Schmidt, Saul Perlmutter, and Adam Rees, the 2011 Nobel Prize in Physics. And this discovery of dark energy came at the end of a tumultuous century. Astronomers had discovered that our Sun was an ordinary star in an ordinary galaxy, nowhere in particular in an expanding universe. More shocking was the revelation that, in terms of matter, all the atoms in all the stars in all the galaxies are little more than cosmic bit players. All the matter we can see appeared to be dwarfed by huge quantities of unseen matter, revealed only by its gravitational pull. And as 1998 dawned, we realized that even this dark matter was significantly outweighed by the presence of the newly discovered dark energy. Two vast components of the cosmos, unseeable and for millennia undetectable. It is currently the biggest question in cosmology. What are these new components of our universe? How do they work? And where did they come from? This video is sponsored by Magellan TV. Question: out of the 100 billion planets in the Milky Way, how many could have the potential ingredients for life? 7? 15 million? 300 million? More than a billion? That's right, excluding Earth, only about 300 million. Including Earth, same answer. And so, my recommendation from Magellan's new documentaries released this week is Other Earths, The Search for Habitable Planets, an exclusive new documentary that dives into the world of exoplanets. It's a great watch and really opened my eyes to how many factors have to be just right for life to exist, let alone thrive. Magellan TV are a sort of Netflix for documentaries, with more than 3,000 videos to choose from on a wide range of topics. And this Christmas, History of the Universe viewers can take advantage of a special holiday offer: buy one, get one free gift cards for an annual membership by clicking on the link in the description. Thanks. On the 29th of May 1919, a total eclipse of the Sun passed over the southern Atlantic. Two expeditions headed by British astronomers Arthur Eddington and Frank Dyson set off to observe this phenomenon. One team headed to Brazil, the other to West Africa. The expeditions were beset by problems, from faulty instruments to weather that refused to cooperate. On the island of Principe, off the coast of Africa, the eclipse was due at 2 in the afternoon. But throughout the morning, Eddington had sat in the pouring rain, the sun not peeking from behind the grey until half an hour before the eclipse. Clouds continued to cross the sky even as it darkened. Eddington busied himself changing photographic plates in the telescope, only glancing momentarily at one of nature's most spectacular sights. Would the observation be a lost cause? Would all this effort be a waste of time? A few days later, Eddington had his answer. And our picture of the universe changed forever. The headline in the New York Times proclaimed "Lights all askew in the heavens," and the little-known Albert Einstein became the most famous scientist in the world. 4 years earlier, during the turbulent years of the First World War, Einstein had published his general theory of relativity. The culmination of a decade's hard work, relativity gave us a new picture of gravity, replacing Newton's forces with malleable space-time. During the war years, relativity was an academic curiosity, but with peace restored, scientists had set out to test the predictions of this new scientific theory. Their goal had been to measure the locations of background stars whose light passed close to the edge of the sun, stars that would be visible when the immense glare of the sun was dimmed during an eclipse. If Einstein was correct, the gravity of the sun should act like a lens, gently deflecting the starlight from its straight-line path. And on the photographic plates obtained in Brazil and Africa, the stars had shifted by the predicted amount. Einstein's theory had triumphed. Whilst the result made him a star, Einstein thought that this gravitational lensing had little practical consequence. Stars were simply not massive enough to use as natural telescopes to magnify the distant universe. Nothing could be. There was nothing in the universe with enough mass to have such an effect. Or at least, as far as he knew. In the 1930s, astronomer Fritz Zwicky was working at the California Institute of Technology. Zwicky was a brilliant scientist with a prickly personality. Combining geometry and profanity, he referred to his enemies as spherical bastards, implying they were a bastard no matter which way you looked at them. But as an original thinker, Zwicky's mind roamed through the mysteries of the universe. He coined the word supernova to describe immense stellar explosions, and realized a superdense remnant known as a neutron star would be left in the ashes. And in 1933, Fritz Zwicky was focusing on the Coma cluster. Located 300 million light-years away, Coma is immense and home to thousands of individual galaxies. This was barely a decade after the realization that the Milky Way was not alone in the universe, and numerous other galaxies exist, scattered throughout the cosmos. Zwicky reasoned that the individual galaxies in Coma were held in their orbits by the gravitational pull of all the other galaxies around it. He realized that by measuring the galactic speeds, he could determine just how much mass was in the Coma cluster, providing a new way of weighing the galaxies. But instead, what Zwicky found was a big problem. The galaxies in the Coma cluster were moving far too fast. With only the gravitational effect of the galaxies in play, each galaxy in Coma should have been travelling sedately in its orbit. With immense speeds of almost 1,000 kilometers per second, Coma should have been tearing itself apart. It was clear significantly more gravity was needed to hold Coma together. What was the source of this extra gravity? With nothing obvious, Zwicky concluded that there must be Dunkel Materie, dark matter, gravitationally binding the Coma cluster. And there had to be a lot more dark matter than the stars we can see. Zwicky's realization that much of the mass in the universe is dark was startling. Questions immediately sprung to mind. How much is there? What is it made from? And how can we measure it? Zwicky's discovery should have set the astronomy world on fire. But instead, there was silence. Possibly because of his brusque style, this notion of dark matter lay buried in the pages of scientific journals. And for the next few decades, astronomers had a new focus: measuring the expansion speed of the universe. By the 1970s, there were new technological advances, large telescopes and sensitive instruments for observing the heavens. And with these, a new generation of astronomers was asking new questions about the universe. For Vera Rubin, the target was large spiral galaxies similar to our own Milky Way. Working with her collaborator Kent Fort, Rubin wanted to understand how these galaxies spin. She had entered astronomy when it was essentially a male-only activity, and she encountered resistance throughout her career, including a lack of female bathrooms in the telescopes she used. But this didn't stop her, as she undertook meticulous observations of the rotation speeds of spiral galaxies. The expectation was that these galaxies were like the solar system, with most of the mass concentrated towards the center. Just like the planets, the speeds of stars in the spiral disk were expected to fall as gravity gets weaker towards the edge. But this was not what Rubin found. The rotation speed of stars did not diminish, but remained roughly the same all the way to the edge of the galaxies. Just like Zwicky, Rubin was left with a gravitational puzzle. What was the source of gravity needed to keep the stars moving at their unexpected speeds? Zwicky's dark matter was back in the spotlight. It was becoming clear that what we could see with our telescopes, the myriads of stars and clouds of gas, were nothing but minor cosmic players. Astronomers were faced with a stark question: is there an entire shadow universe of dark matter out there? The evidence was growing, and it was now they turned to Einstein's seemingly inconsequential theoretical prediction made more than half a century before. They turned to gravitational lensing. Indeed, Zwicky had suspected this also years before. He had reasoned that with the extra dark matter, galaxies and clusters of galaxies would be powerful gravitational lenses. But it took until the 1960s for scientists to really come to grips with this concept and find a point of energy staggeringly huge enough to properly observe. Quasars. Appearing as little more than points of light through the most powerful telescopes, they shine with the brightness of more than 100 trillion stars. It was realized that quasars were powered by supermassive black holes. The gravitational pull of these black holes accelerates in-falling material to close to light speed. As it swirls into the inner regions, matter crashes together, heating it to immense temperatures. And it is this accreting disk of matter that glows so brightly. And with this immense brightness, astronomers could spot quasars at incredible distances, many billions of light years from Earth. By the 1970s, with their observational approaches honed, finding quasars was routine. Then, in 1979, one quasar, uninspiringly labelled Q0957+561, provided a puzzle. Astronomers realized that this appeared to be two quasars very close to each other in the sky. This is not too unusual, but it was found that these two quasars appeared to be identical. The astronomers realized that they were seeing double, a gravitational mirage. Between us and the quasar sits a massive galaxy, and its gravity distorts our view, producing two separate images of the single object. Zwicky was right again. and more than 80 years since it was first observed under the clear skies of Africa and Brazil, gravitational lensing had found its purpose. In the decades that followed, thousands of gravitational lenses have been discovered. Many of these are due to individual galaxies, but the most spectacular are produced by the immense gravity of gravity clusters. Distant galaxies that would be too faint to see in our telescopes are magnified by these cluster lenses, appearing as immense arcs. Every instance of gravitational lensing provides an opportunity to measure how much mass is present by measuring the distortion. And the conclusion is always the same. There is a lot more mass than that visible as stars and gas. In fact, most of the matter in our universe is completely dark. But it wasn't just gravitational lenses that revealed the ubiquitous presence of dark matter. Everywhere astronomers looked, dark matter was needed to explain their observations. From immense flows of galaxies through the universe, to the presence of gas in galaxy clusters that had been gravitationally squeezed by dark matter was everywhere, and it dominated the gravitational pulls of the cosmos. Finally, we came to realize that it had shaped our universe. Looking up at the night sky, the black is filled with stars. Some form patterns. For millennia, humanity has interpreted shapes from these arrangements, creating meaning from their placement. From the ancient Egyptians to the Inca, these constellations have captured our imaginations. But behind these simple patterns lurk complex, incomprehensibly huge clusters. Many billions of light years away, many billions of light years across, with many billions of stars and galaxies within them. The Great Wall, the Giant Arc, and indeed, where we live, Laniakea. And so, it was in the 1970s that astronomers started to chart the locations of galaxies. They began to create an atlas of the universe. The idea was simple. A measurement of cosmic speed due to the expansion of the universe reveals a galaxy's distance. But this meant collecting and analysing the light from many individual galaxies, a laborious task. Dedicated programs were established to measure galaxy light, with one of the first being the CFA Redshift Survey, based at Harvard's University Center for Astrophysics. And, as measurements were gathered, the structure of the universe was revealed. It was clear galaxies were part of a cosmic web, with individual clusters linked with filaments. Embedded in this structure were huge empty regions, known as voids, giving the universe a sponge-like appearance. By the mid-1990s, two astronomers, John Huchra and Margaret Geller, had analysed the light of 18,000 galaxies. They labelled immense structures such as the Great Wall and the Stickman, each composed of thousands. More modern surveys of galaxies, including the 2DF Galaxy Redshift Survey and Sloan Digital Sky Survey, have mapped more than 1 million, revealing clusters, filaments, and voids throughout the universe. But this raised a question. Where did all this cosmic structure come from? Astronomers knew that the fiery birth of the universe in the Big Bang left it featureless. The hydrogen and helium forged in the first few minutes was smoothly spread through the cosmos. But underlying this was dark matter. For, in the time before the first stars, when the cosmos was truly dark, dark matter was starting to stir. In the beginning, the matter in the universe wasn't perfectly smooth. A burst of expansion, known as inflation, in the earliest moments had written very slight ripples in the universe. Some places in the early universe were slightly more dense than others. Other places were less dense. And even though these density differences were tiny, they were enough for gravity to do its work. And this gravity from very slight overdensities started pulling material in. Matter began to flow, and hydrogen and helium gas came along for the ride. After 100 million years, densities grew and gas pooled. Chunks of hydrogen and helium fragmented out of the clouds. From this cooling and collapsing gas, the first stars were born. And in the universe, again, there was light. Forming in the dense knots of dark matter, these infant stars lit up the sites of the first galaxies. Over the billions of years that followed, dark matter drew in more mass, with growing quantities of dark matter accompanied by more stars and gas. And so, 14 billion years after the birth of the universe, these fully formed galaxies sit at the hearts of immense halos of dark matter. Unraveling the process of galaxy evolution is complex. Astronomers need to understand the ebb and flow of gas, the life cycles of stars, and the formation of black holes. Combining all this physics is difficult, so astronomers turn to supercomputers to solve the highly coupled non-linear equations. It is now routine for astronomers to generate synthetic universes, watching the interplay of the numerous processes that have shaped our cosmos. The resultant insights are astounding and beautiful, watching galaxies emerge from the early cosmic fog. And quite clearly, the dominant factor is dark matter, providing the framework against which galaxies can evolve. Without it, it would have been extremely difficult for stars and galaxies to begin to form. Astronomers realized that dark matter had to have some particular properties to build cosmic structure. As well as its gravitational influence, they realized that matter must move relatively sluggishly through the universe, as too much speed would make it disperse rather than clump. They called it cold dark matter, with the cold referring to its slow speed. And so, dark matter clearly played a huge role in the development of complexity in the universe. But one huge question remained. Just what is it? In 1930, Wolfgang Pauli was faced with a problem. Radioactivity had been studied for several decades, but one kind of particle decay was behaving strangely. This beta decay appeared to be relatively simple, with an atomic nucleus spitting out an electron, or its antimatter cousin, the positron. But for a collection of identical atomic nuclei, the particles that got spat out had different properties. Some sped away at high speed, others moved more slowly. This meant that some had high energies, whilst others had lower energies. How could this be? The conservation of energy demanded that each of these ejected particles should have the same speed. Pauli wondered if the conservation of energy was being broken, a distressing conclusion he couldn't stomach. Instead, he suggested another thing is also spat out during beta decay. Another particle that carried away the seemingly missing energy. Named the neutrino, this purely hypothetical particle had some peculiar properties. The fact that it did not collide with atoms told us it wasn't a photon, the particle of light. It was something else, something different. It wasn't until the 1950s that Pauli's hypothetical particle was finally detected in sensitive experiments set up next to nuclear reactors, a prestigious source of neutrinos. Astronomers realized that the universe was full of neutrinos, most produced in the frenetic nuclear reactions in the earliest epoch of the universe. Given that they barely interact with matter, it was suggested that these neutrinos could be the dark matter. But as experiments improved, it was realized that neutrinos are just too minuscule and too fast to account for dark matter's gravitational dominance. Physicists would have to continue the search. What else could be dark enough to be dark matter? What else could be massive enough? One possibility was quickly ruled out: dark matter could not be made of atoms. It is possible to hide atomic matter, making it dark by cooling it so that it doesn't emit any energy. We could imagine dark matter in the form of super-chilled clouds of hydrogen between the stars, but the cooking of elements during the Big Bang puts strong limits on how much atomic matter there can be, and it's simply not enough to account for all that is needed. Another obvious candidate is black holes. These are clearly dark, being the ultimate trap for light, and we will only feel their presence through their gravitational attraction. Possibly, these black holes were born in cracks in space-time, defects that existed in the first moments of the Big Bang. Huge numbers of these primordial black holes could course between the stars. But, as Einstein realized, the gravitational pull of each black hole would make it behave like a gravitational lens, distorting and focusing light of the more distant universe. As a black hole passes directly in front of a more distant star, the resulting magnification would, for a period of around a month, make the star appear brighter. Even if all dark matter were in the form of black holes, the chances of such a passage is exceedingly small. However, in the 1990s, astronomers were searching for these rare brightening events. But after more than a decade of hunting for the gravitational microlensing, the result was disappointment. Dark matter cannot be composed of black holes. Whilst astronomers were gazing skyward, particle physics were hunting for dark matter in the world of the subatomic. Through the course of the 20th century, they had unraveled the fundamental nature of matter, finding the particles from which mass and forces are constructed, comprised of quarks and leptons, photons and gluons, as well as the more esoteric W and Z bosons. This zoo of particles was rounded off in 2012 with the discovery of the Higgs boson. This standard model of particle physics has proved to be a great success. It accurately accounts for the tumult of particles pouring out of the immense collisions at the Large Hadron Collider and other particle physics experiments. Despite this, we know it must be incomplete. Missing from the standard model of particle physics are at least two key aspects of the universe. It can account for the strong and weak nuclear forces and electromagnetism, but gravity is still resisting being added to the quantum world. And also missing is dark matter. Nowhere in the possible particles is there an obvious place for dark matter to be hiding. Knowing the mathematics of the standard model must be incomplete is a potential goldmine for theoretical physicists. They can explore how the mathematics can be unfolded and extended, and every new addition to the standard model adds room for candidates for dark matter. But just like there are many directions you can wander off from a single point, there are many potential paths you can take when extending mathematical ideas. One of the promising ideas was proposed in the 1970s, just as the mathematics of the standard model was crystallizing. The key problem was the strong force, the force responsible for binding quarks into protons and neutrons, and gluing protons and neutrons together in atomic nuclei. As originally derived, the mathematics allowed the strong force to break a possible symmetry in the universe, something known as charge parity violation. But all experiments appeared to show the strong force was well behaved, refusing to break the symmetry. The mathematics needed an extension known as the Pache-Quinn mechanism to shore up the symmetry. And it was the presence of this mechanism that implied the existence of a new member of the zoo of fundamental particles. Nobel Prize winner Frank Wilczek dubbed this new particle the axion, taking the name from a popular washing detergent as it cleaned up several problems in physics. Whilst these axions hypothetically individually possess a tiny amount of mass, they would be extremely numerous and would only interact with atomic matter very rarely. It appeared to be an ideal dark matter candidate. But, to date, not a single axion has been detected in the uncountable number of high-energy collisions at the Large Hadron Collider. It remains a contender. Other approaches to extending the standard model of particle physics have yielded other possibilities for dark matter. Supersymmetry doubles the particle zoo, As well as electrons and quarks, there are selectrons and squarks. There are also photinos, winos, and xenos. Perhaps hidden within this larger family is the sought-after dark matter. Different mathematical ideas have sterile neutrinos, massive cousins of those that we know, or possibly hooperons, or cueballs, or the latent Higgs field, or asymmetric dark matter. The problem remains that physicists have a shopping list of possible candidates, but as yet, no experimental result suggests that we are even on the right path to understanding what dark matter is. Finally, in their quest, some particle physicists have joined with the astronomers to look back to the heavens. Several of the mathematical ideas for dark matter suggest that it might self-annihilate, in the same way that an electron and positron can collide and transform into two photons. And if it does self-annihilate, then perhaps we can detect the high-energy radiation that would be emitted. Telescopes are currently trained on the locations where we think dark matter density would be the highest. And there is a potential signal, an unexpected glow of high-energy gamma rays from the galactic center. It is still not clear whether these are from mundane astrophysical sources or possibly could reveal the discovery of dark matter. And only time will tell. Though the question still lingered on at the frontier of cosmology, at the end of the 1990s, clear progress was being made, with many possibilities opening up. The composition of the universe was getting a little less blurry. And then, as sometimes happens in physics, a result came along that totally upended what had come before. We opened this story with the discovery of the other dark component, dark energy, in the closing years of the 20th century. As the shock of this discovery subsided, questions began to grow. Just what was this new, dark, mysterious stuff of the universe? Whilst dark energy sat at the bleeding edge of modern physics, it was realized that its story was much older. And so, we return to Einstein. With his general theory of relativity in hand, he wanted to deduce the equations that govern the dynamics of the universe. But something wasn't right. Einstein felt that the universe was static and unchanging, the same now as it had always been. His equations, however, presented a different picture, that the universe should be a dynamic place, changing and evolving. Perplexed by this, he explored his equations, wondering if he'd missed something. He realized that there was a term which could act like an anti-gravity, and as there seemed to be little evidence for anti-gravity, he assumed it was zero. But he still wondered, what if it wasn't? Through this, he found a remarkable effect, that he could get this anti-gravity to counter the dynamic nature of his equations and make his model universe static. And after introducing this cosmological constant, and being pleased with himself, he told the world. But not all the world agreed, especially the Russian physicist Alexander Friedmann. He held no favoritism for a static and unchanging universe, pointing out to Einstein that the notion of a dynamic and expanding universe is much more likely. Initially, Einstein objected to Friedmann's conclusion, but eventually was convinced. And so, he threw this cosmological constant into the scientific waste bin. He later, supposedly, called it his biggest blunder. And this dismissal meant that no one considered the notion of a cosmological constant for many decades. And whilst these theorists were grappling with the mathematics of an expanding universe, astronomers were charting the heavens. At the Mount Wilson Observatory, Edwin Hubble was using the world's largest telescope, the 100-inch Hooker, to measure the distance to galaxies. Hubble's goal was to identify particular stars, known as Cepheids. As he could calculate their true brightness, these standard candles revealed the distance to their host galaxies. Hubble combined his galactic distances with galactic speeds, measured with Doppler shift, and found something quite peculiar. The more distant the galaxy, the faster it was moving. And other than the closest galaxies, all were moving away. Whilst he didn't realize it, Hubble had discovered conclusive proof. The universe was expanding. And over the remainder of the 20th century, astronomers have refined Hubble's observations. Huge observing programs were organized to chart the universe, measuring the distances and velocities of many thousands of galaxies. The goal was a single number, known as Hubble's constant, which was a measure of the rate of universal expansion. And this brings us back to the very beginning of our story. Modern surveys of the heavens, with supernovae acting as standard candles, finally revealed that this universal expansion is accelerating. And so, again, we are left to ask the question, what is the dark element of the cosmos causing this effect? To begin with, it cannot be matter or radiation, as these slow down expansion. To speed up expansion, something else is needed, something that seems like an anti-gravity. Astronomers called this mysterious stuff dark energy. But in reality, Einstein's cosmological constant was back. The existence of dark energy was not the only surprise. When the cosmic accounting was completed, astronomers realized that all the atomic matter, the stars, the planets, the immense gas clouds in galaxies, comprised less than 5% of the universe. Dark matter, the scaffolding of the cosmos, is about 25%. Dark energy made up the remainder, 70% of the universe. Many physicists were baffled. Why is the universe completely dominated by this mystery stuff? And in the 2 decades since its discovery, the evidence for the existence of dark energy has become overwhelming. Its presence is written into the distributions of galaxies spread over billions of light years. It is also written into the cosmic microwave background, the radiation left over from the fiery start of the universe. And it has seemingly bizarre properties. As the universe expands, matter and radiation thin out. Dark energy, however, appears to remain constant. This means that in the early universe, matter and radiation dominated, and the presence of dark energy had no impact. But about 5 billion years ago, the tables were turned. Matter had thinned out to the point where dark energy became dominant, and the acceleration of cosmic expansion began in earnest. This accelerated expansion dilutes matter even faster, meaning the future universe will be completely dominated by dark energy. In about 100 billion years, this expansion will have carried all galaxies outside of our local group beyond our cosmic horizon. Eventually, the universe will again return to darkness. In quantum mechanics, empty space is not truly empty. Heisenberg's uncertainty principle allows energy to fluctuate in and out of existence on tiny scales. This quantum nature of the vacuum provides empty space with a tension that can be measured in experiments. And whilst our cosmological equations offer few clues to the nature of dark energy, it can tell us something. Unlike normal gas that possesses an outward pushing pressure, dark energy has a tension that pulls. And there is one thing in nature that possesses this similar tension: the quantum vacuum. But problems begin when physicists try to calculate just how much energy there is in such a fluctuating vacuum, as their answer is simply ridiculous. The mismatch between their mathematics and the amount of energy observed in dark energy differ by an immense factor of 10 to the power of 120. Some have called this the worst prediction in all of physics. but it signals that if the vacuum is responsible for dark energy, we have a lot to learn about its true properties. And that is just one suggestion. Indeed, with so little in terms of observational evidence, proposing ideas for the nature of dark energy has become a theoretical playground. Various fields have been proposed, some aloof, sitting in the background of the universe and doing their own thing. Others have wondered whether dark energy is related to the other bout of accelerated expansion in the life of our universe. The epoch of inflation is thought to have taken place when the universe was about 10 to the minus 35 seconds old. The driving force behind inflation was another mysterious and hypothetical field, the inflaton. Could dark energy be a resurgence of the inflaton? The best we can say is maybe. Of course, there is one other invisible element controlling the cosmos, so the question has been asked. Are dark energy and dark matter related? Again, physicists can derive mathematical models where there are interactions in the dark sector, where dark matter and dark energy possess a common origin. In fact, the dark sector could potentially host its own physics, as rich as those in the atomic world. But, with the limited observational evidence, we are again stuck in the world of theory. Clearly, more observations and measurements are required. A whole host of experiments are underway, with many more planned for the immense telescopes that are currently making their way from drawing board to reality. In Chile, the 8.4-meter telescope at the Vera Rubin Observatory will turn its eye to the sky in 2022. The 40-meter European Extremely Large Telescope, also in Chile, will have its first light in 2024. The key goals of these and other telescopes is to uncover the mysteries of dark matter and dark energy. This includes searching for the signs that dark energy might not be exactly Einstein's cosmological constant. Perhaps dark energy has evolved and changed over the billions of years of the universe. Maybe it has decayed into matter and radiation. These would provide new clues to the true nature of dark energy and open new avenues of research to unravel its physics. However, as of today, all observations suggest that dark energy appears to be precisely Einstein's cosmological constant, unchanging over the life of the universe. But this sends a shiver down the spine of cosmologists, as it might mean that the cosmological constant is uncrackable. Just a part of the universe, a fundamental property of space, without an origin to understand. Going even further, for some, failure to fathom the nature of dark matter and dark energy represents a failure of the fundamental laws of physics. They argue, instead of hunting the heavens and particle accelerators for physical substances, perhaps we should look closely at our cherished theories. For example, what if gravity is only approximated by Einstein's theory of relativity, and the truth has yet to be discovered? This could mean that gravity behaves strangely on large scales, not simply getting weaker. This too could account for the rotation curves of galaxies, the gravitational lensing of light, and the accelerated expansion without the need of a physical dark matter or dark energy. But as yet, all contenders have failed to match the success of Einstein's mathematics in explaining the universe. The search continues. And so, today, our universe is completely dominated by its dark side. And in truth, it remains mysterious. If dark matter and dark energy are physical things, we need to determine their true properties to understand their place in the universe. Without these, questions like where they arose in cosmic history and how they impact the fundamental nature of the cosmos will remain difficult, if not impossible, to answer. But if the dark side is only a mirage due to the limits of our physical theories, then an even bigger upheaval to our understanding is on the cards. Until then, the dark side of the universe holds the keys, and it is holding them tightly. you've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.